Hey guys, so this is kind of rounding out Chapter 5, and there's three basic principles that we want to deal with. The first of those three principles, this would be 5.6 through 5.10. I got a 10. All right. So the principles that we want to discuss and manage here in the second half of circular motion, the first thing we want to acknowledge and deal with is what's called Newton's law of universal gravity. Newton's law of universal gravity. And this deals with the fact that, or gravitation. And so this, well, we have Newton's law of universal gravitation. And in that law, we learn that there is gravitation or pull of gravity between any two objects that have mass. Which, when we calculate that, we need to recognize a couple of things. We need to recognize, A, the more massive something is, it certainly is going to have more pull. You know, I can't make a fly orbit around me, although technically they do kind of do that sometimes, but I can't make it follow my mass. But yet somehow the sun makes the Earth and the entire solar system orbit around the sun. So it feels like mass has to have some impact on how much gravity things are experiencing. The other thing to recognize is that, you know, the further we get away, it seems like you either have to have really big masses or you're just not feeling much pull. You know, as we get further and further away from the sun, if we travel out in space, the sun seems to matter less and less to us in terms of its pull and gravity. And if we're really small, pretty soon the sun's gravity just isn't there to really pull us around. Now, if we're really massive, like Jupiter, you know, we can be really far away and still feel a really strong pull from the sun. And so Newton's law of gravity, as he went through and calculated these different relationships, we can say the force from gravity, and I'm going to use a big G here to kind of say this is not Earth on the surface, trying to figure out gravity. This is really in between any two objects. It could be the Earth and a person, but it's universal. Equals big G times M1 times M2, so that's mass 1 and mass 2, the two objects, divided by the radius between them squared. Now you got to understand a couple of things. When we talk about the radius between two objects, sometimes that radius is really small. It might be, for instance, my radius is relatively small relative to the Earth's radius. So when we talk about the measure of my radius and the Earth's radius, you know, we're really just talking about from center to center, and we want to be as close as we can. So if you can imagine, here's the Earth, right? We'll call this the Earth, and we'll put the moon over here, okay? The moon. And when we talk about the distance between them, truth is we can just measure the distance between the two surfaces. If we want to be hyper accurate, we would measure from the center of the Earth to the center of the moon. But that's a calculation that's not always the same, because the moon doesn't always follow a circular orbit. We're going to talk more about that in a minute, but it's not universal. So we want to be, you know, close, and so we're going to use some approximations. Typically, if we're talking about planets, we're going to talk surface to surface or average distance between them. But there is one thing that's really important, and this was one of Newton's discoveries. This is universal gravitational constant, big G. If I look in the front cover of the textbook, or you guys look in the useful information, find that the gravitational constant, big G, is 6.67 times 10, or e, to the negative 11th. And then its unit is actually one of those funny units where its unit is really based on making the equation valid. You know, we have a mass times a mass divided by a radius squared, and we're supposed to end up with force. So the unit has got to be newtons times meters squared over kilograms squared. Meters squared over kilograms squared. That's just about making the unit cancel out appropriately. If I give you two masses and a radius, you should be able to tell me how much force there is between those two things in terms of gravity's attraction. Now, most of the time when we talk about two masses, you know, if we talk about me and the person next to me, yes, technically there's a gravitational attraction between the two of us. However, it's not significant relative to the gravitational force of attraction between me and the Earth. So you don't feel other people, their gravity pulling you to the side, because we're around such a massive object that's always going to win that force vector competition. All right. The second law or second policy or thing that we need to deal with has to do with this formula and to do with circular motion. If we have something in a circular motion, we know that to get a circular motion, your total force along the radius has to equal mv squared over r. Now, if I want to put a satellite in orbit around the Earth, right? Here's the Earth, and there's a satellite going around. We'll make it look a little bit more like a satellite. As it's going around the Earth, we don't want to always have to be giving, speed to this and driving the satellite the entire time. We want to be able to save on fuel. And so what would be ideal is if we could get it going a certain velocity, okay, getting it going a certain speed around the Earth, and then just allow the satellite to fall towards the Earth at that speed. If the rate at which it is falling is the same as the rate of curvature of the Earth, then literally the Earth's fading away and the satellite is falling along that curve. And that's what we get, this stationary orbit, this idea that we can have it be a stable orbit around the Earth. In order to do that, we need gravity, the gravity between the satellite and the Earth, to match the centripetal force. So what we end up with, this has to equal the gravitational law, which is big G, m1, m2 over r squared. Now something here that's really important is this mass right there is the mass of the satellite. So the mass of the satellite gets to cancel with the mass of the satellite. Now m1 and m2 could be the Earth and the satellite, or the satellite and the Earth, but they're the two masses. What matters here is that we get v squared over the radius equals big G times, I'm going to put me, all right, for mass of the Earth over r squared. Now this radius would cancel the square, leaving me with the velocity squared equals g times the mass of the Earth over the radius. If I want to get this v alone, all I have left is to square root, and this is the satellite velocity equation. So the velocity of a satellite that's going to orbit the Earth or another planet would be the square root of big G times the mass of that planet. We're using Earth, but we could use the Moon, we could use Saturn. We want to go around those things. We need to use their mass divided by the radius of orbit. Okay? Not the planet radius. Okay? It's not the radius, and it's or the height, the altitude, or the altitude. It's both. What that means is, when we talk about this radius, we have to measure from the center of the planet all the way out to your satellite, which means you're going to have to add the altitude to the actual radius of the planet. Those are going to give you your total deal there. Those answers are typically around the Earth. We're going to be between 6 and 7 or 8,000 meters per second. We've got to be moving pretty dang fast to keep a satellite up around the Earth, falling at that right rate. The last thing we need to talk about is Kepler's laws of planetary motion. Kepler had 3 laws. The first law is that planets orbit in ellipses, not circles. People for a long time believed that the planets went around the sun in a circle. He proved that it was elliptical. Now, when we say it's elliptical, a lot of people think of this shape, right? And here's the sun at one of the foci. All right, and then there's the Earth going around it. It's not that elliptical. It's almost circular. It's pretty dang close to circular. So think a little bit more of just a poorly drawn circle, okay? That's clearly a little fatter than normal. What that does is it actually brings the sun closer to the center, okay? That foci is actually pretty close to the center. So first law, we travel in orbits that are ellipses. Second law, it's called the law of areas. When we are close to the sun, we go pretty fast, okay? And there's an area, so say that we go for 3 days, or let's call it 1 month. Okay, we go for 1 month. there's an area that we will carve out in space as we travel 1 month around the sun. Kepler's second law says that even when we're far away, okay, that because we're further away, we move slower. But moving slower at a greater distance away from the sun means that the area at the in 1 month when we're close to the sun, and the area in 1 month when we're away from the sun will be equal. So any period of time in our rotation or our orbit around the sun, we have the same area being carved out of space. So equal areas. And then we have our third law, which is the law of periods. Okay? And we're going to try to make this as simple as I can. There are lots of different ways to describe this, but it has to do with understanding there's a direct link between how far you are away from the sun and how long it takes you to get around. The closer you are, obviously you're moving faster, and so it would make sense that you're going to get around the sun much quicker. Whereas if you're far away from the sun, you're going to expect to take a lot longer to get around. Well, Kepler's law, there's different versions or simplifications of it, but the one that I typically use and try to make sure that we use here as well is that the time or the period for one object to orbit around divided by the time for a second object to orbit around. So this is a comparison law. Okay, so if you know how long it takes for the Earth to get around and you want to know about Neptune, this would be an example of a formula you could use. That ratio squared will equal the radius of the first object divided by the radius of the second object for their orbits cubed. This is going to allow us to make calculations about how long it takes to get around something, or perhaps how far away an object is based on how long it takes it to get around the sun. That allows us to figure out a lot about how many light years away something is without actually measuring or flying out there to figure it out. So hopefully this gives you a little bit of understanding of how Newton's gravitational laws has changed the way we do astrological or astronomical physics and some of the calculations that we can make. All right, good luck. We'll see you in class.